So in the last class we discussed about first order reaction. Okay, if you take a first order reaction of this type, A giving some reactant A which reacts to give product, some product. Okay, now if this is the reaction and A naught is the initial concentration of the reactant and AT is the concentration of the reactant at the time t, that is remaining concentration. Okay, remaining concentration of reactant at time t. If these two informations are known, then you can calculate the rate constant for this first order reaction. K1 equal to, we can write in logarithmic form like 1 by t. This is actually called the integrated equation. Okay, K1 equal to 1 by t ln initial concentration of the reactant over concentration of the reactant at time t. Okay, so this is the rate constant expression. You can also write in log base 10, in terms of log base 10, like 2.303 over t log base 10 initial concentration of the reactant over concentration of the reactant at time t. You can also write like this, right? Then in the last class we also discussed the expression for half-life period. I have told you what is half-life period. Half-life period is nothing but the time taken for 50% completion of a reaction. Time taken for 50% completion of a reaction. Anantha Krishnan, turn on your camera. All of you turn on your camera. Yeah. Keep it in the same mode, okay? And listen properly. So rate constant expression is this, and we also derived the expression for half-life. Half-life period for first order reaction is ln 2 divided by rate constant for first order reaction, ln 2, or you can also write like 0.693 divided by K1. So this is the expression for half-life period. Okay, then I also gave the expression for concentration of the reactant at time t. You can calculate the concentration of the reactant at time t by using this expression, that is A naught into e power minus rate constant for first order reaction into t. Using this expression we can calculate the concentration of the reactant, okay, at any time t, provided you must know the value of the rate constant for the reaction and the initial concentration. Okay, then we discussed about degree of dissociation here, alpha. Degree of dissociation. Okay, in the last class I gave the expression, but I missed one important term there. Listen, students, alpha is equal to initial concentration of the reactant minus concentration of the reactant at time t. Okay, I gave this this particular these two terms, but I forgot to give the term that is divided by A naught, because degree of dissociation is nothing but the fraction of the reactant molecule dissociated. Okay, so in the degree of dissociation you must put A naught minus AT by A naught. Okay, I forgot to give this A naught in the denominator in the last class, so just note down. So now if I substitute this value here, we will get the expression for degree of dissociation for first order reaction. Okay, let me write to the next page.
Sir, 1 second.
Yes, ma, yeah, note down. So degree of dissociation alpha is equal to, I'll keep this A0 as such, minus, in the place of AT, you know very well the expression for AT is A0 into e power minus K1 into T, this T, over concentration of A0. So in the numerator you take A0 as common, A0. So what is left with is 1 minus e power minus K1 into T. I took A0 as common in the numerator, divided by A0. So A0 cancels. So you will get alpha is equal to 1 minus e power minus K1 into T. This is the expression for degree of dissociation for a first order reaction. Note down. So if you know the rate constant, okay, then you can calculate degree of dissociation, okay, for a particular time of the reaction. Suppose after 10 minutes, what will be the degree of dissociation of the reaction? Yes, you can calculate. Okay, note down. Then, so these things we discussed in the last class. Okay, and we also discussed the graphical representation, right? I'll just make you to remember whatever we discussed in the last class. Graphical representation of first order reaction. If I plot concentration of the reactant, okay, at different time versus time, students observe carefully. For zero order reaction, okay, you will get a straight line with a negative slope, whereas for first order reaction you will get a curve, okay, exponential decay curve. Okay, the concentration decreases exponentially because you know the expression AT equal to A0 into e power minus K1 into T. This is the expression for rate constant for concentration of the reactant. Okay, if I put time equal to 0, time 0 means here. At time 0, if I put 0 here, this entire power becomes 0. E power 0 is 1. Therefore, at time 0, concentration of the reactant is nothing but equal to initial concentration. So this is nothing but initial concentration. Okay. Then, as the time progress, as the T value increases, I can say in the other way. If T value increases, what will happen? We have e power minus there. So the concentration decreases exponentially. Okay, so remember this is very important, this first plot. And what about the second plot? If I take logarithm, if I plot logarithm of A, if I plot logarithm of A, ln A, and if I plot versus T, you know very well, ln A, last class I gave this expression, okay, equal to K1 into T, see we are deriving from this expression. I'll just write the rate constant expression once, 1 by T ln, so that you can easily remember. Okay, we have to rearrange this, so bring this K1 T here, you will get K1 into T, then you will get ln A naught minus ln AT, bring the ln AT to the left hand side, so we have ln A naught in the right hand side, and bring the K1 into T in the right hand side. Okay, now if I plot ln AT in y-axis, see here, the ln AT in y-axis and the time in x-axis, you will get a straight line with a negative slope. You will get a straight line with a negative slope, and slope of this straight line will give you the value of rate constant minus K1, or I can write K1 equal to negative of the slope of the straight line. Note down. Okay, this plot also I gave in the last class. Then I have given one more plot, so you have to notice carefully what we are plotting in y-axis and what we are plotting in x-axis. If I plot log base 10 AT, okay, see in the second plot I have plotted ln AT. Now I am plotting log base 10 AT versus T. Yes, here also you will get a straight line with a negative slope. And what is the slope here? Here slope is equal to minus k by 2.303 will be there, or k is equal to minus 2.303 times slope. Okay, so you can calculate the rate constant for first order reaction, right, either using this plot or that plot. But when 2.303 should be introduced, when it should not be considered. Okay, that is depending upon the quantity that we are plotting. Students, observe carefully. In the second plot, in y-axis we have plotted ln AT. In the third plot we are plotting log based on AT. Okay, yeah, students, turn on your camera, everyone. Turn on your camera. So, graphical plot and all we discussed. What I'm going to do now is, suppose if gas phase reactions are given, students, observe carefully. Sometimes the reaction may occur in a gas phase. Whenever reaction occurs in gas phase, people normally won't measure concentration. Instead of concentration, they'll measure the pressure. Okay, they'll measure the pressure of the system at different time interval. For example, let us consider a reaction of this type. See, I'll take some reactant A which is in gas phase. Assume that this reactant reacts to give some product B and another product C. I have two products now. Okay, and let us consider this reaction is a first order reaction. It's a first order reaction. That means the rate constant for this reaction K1 equal to 1 by T ln initial concentration of the reactant over concentration of the reactant at a time T. This is the rate constant expression. Now, see, since it is a gas phase reaction, okay, assume that this data is given. Suppose instead of concentration, some data are given like this. Say, for example, I'm giving you time and total pressure of the vessel. Suppose I'll take a vessel. Okay, initially we'll take the gas A. Assume that I have only gas A. Right, so in the vessel we have only A molecules, and I'll fix a pressure gauge here, pressure gauge. Using the pressure gauge, you can measure what is the pressure inside the gas, inside the container. Okay, so at time zero means reaction is not yet started. When reaction not yet started, inside the vessel you have only A molecules. So at time zero, okay, the pressure of the vessel, also called total pressure, at time zero, the total pressure is only due to A molecules. Okay, let us take that total pressure as Pi. What is Pi? Pi is the initial pressure of the vessel. Okay, or the gas that is present in the vessel. At the time zero, students, observe carefully, at time zero we have only A molecules. Only A molecules are there in the container. So the initial pressure is nothing but pressure due to A molecules. Now, suppose we'll start the reaction. If we start the reaction, what will happen? A molecule starts to react and forming B and C. So concentration of A decreases. Okay, A molecules, number of A molecules starts to decrease, and number of B molecule and C molecule, okay, they starts to form, so they starts to increase. Now, if I give total pressure at a time T, students, observe carefully, at 5 minutes, say for example, at 5 minutes, see from A, say for example, some amount of A is reacted, some partial amount. So at a time t, inside the vessel we have gas A, we have some amount of gas B, we have some amount of gas C also. Okay, now the pressure due to A is nothing but partial pressure of A, because now you are having a mixture, and the pressure due to B is nothing but partial pressure of B, and the pressure due to C is nothing but partial pressure of C. Okay, if I add all these partial pressure, I'll get what is called the total pressure. That total pressure is given here. Students, observe carefully. At the beginning of the reaction we have only A, therefore the total pressure, right, it is given as Pi. Pa is nothing but pressure of the gas A alone, because initially we have only A molecules. Then once the reaction starts, okay, A molecule, some number of A molecules, okay, will form B and C. Therefore at the time t, you will be having A molecules, B molecules as well as C molecules in the container. What we measure is the total pressure. Okay, total pressure is the sum of the partial pressure of A, partial pressure of B and partial pressure of C. Okay, now if these two data are given, students, observe carefully, if these two data are given, how to calculate the rate constant? Okay, yes, we can calculate the rate constant by using this idea. So what I'm going to do, students, observe carefully. Listen, so we need the initial concentration of the reactant, and we need the concentration of the reactant at a time t. If you know these two values, yes, you can calculate the rate constant. Okay, initial concentration of the reactant is directly proportional to initial pressure of the vessel. Why? Students, concentration and pressure, yes, you can relate, they are directly proportional, because you know very well the ideal gas equation PV equal to nRT, okay, or P equal to N by V into RT, or I can write N by V is directly proportional to P. N by V is nothing but concentration. It's nothing but concentration. So concentration is directly proportional to pressure. Okay, so initial concentration of the reactant is directly proportional to initial pressure. That is total pressure at the beginning of the reaction. Why? Because at the beginning or at time 0 you have only A molecules in the vessel. Therefore total pressure at time 0 is nothing but, or it is directly proportional to initial concentration of the reactant. Now what is the concentration of the reactant at time t? Students, observe carefully, this is a very important point. Concentration of the reactant at time t, it is directly proportional to partial pressure of the reactant A in the mixture. But this is not given. This is not given. What is given? Only the total pressure at a time t is given. I have told you total pressure is nothing but sum of partial pressure of A plus partial pressure of B and partial pressure of C. Okay, but what we want is partial pressure of A alone. How to get that value? Yes, it is very simple actually. See, what is the reaction given? A giving B and C. All are gases. Okay. Now, at a time t, at a time equal to 0, students, observe carefully. Time 0 means we have only A molecules. So, whatever pressure given, Pi is the pressure measured at time 0. It is only due to A molecules. So, at time 0, whatever pressure is there, that is due to A molecules. B and C molecules are not there in the container. Now, at a time t, assume that the reaction starts, okay, at one particular time, we measure the pressure. Okay, at time t, see from the A molecule, some number of A molecule reacts. Okay, so what will happen? Pressure get reduced. Pressure due to A get reduced. Okay, let us assume X fraction of A is reacted. Students, observe carefully. From initial pressure, let us take some X fraction is reacted. According to the reaction, see what is the reaction? A giving B plus C, right? When one molecule of A react, you will get one molecule of B and one molecule of C. So if X fraction of A reacts, you will get X fraction of B and X fraction of C. Okay, so Pi minus X is nothing but partial pressure of A in the container. Pi minus X is nothing but partial pressure of A in the container. We want this actually. We want this partial pressure of A. Initial pressure is given. X is not given. Okay, but total pressure at time t is given. Okay, what is total pressure? Total pressure is nothing but sum of partial pressure of A plus pressure due to B, partial pressure due to B plus partial pressure due to C. If we add all these things, that is nothing but total pressure at a time t. Okay, minus X plus X you can cancel. Okay, so what is the value of X? X is equal to total pressure at a time t minus initial pressure, that is at time 0. That is the value of X. Now we got the value of X. Substitute this value here. You will get the PA, partial pressure of A. So what is the partial pressure of A? Partial pressure of A is equal to Pi minus X. In the place of X, I will put this. What is X? X is nothing but Pt minus Pi. Now if I simplify this, I'll get Pi. We multiply this by minus sign, so you'll get minus Pt. Minus of minus become plus Pi. Plus Pi. So Pi plus Pi is 2 Pi. So you'll get 2 Pi plus, minus 2 Pi minus Pt. What is this? This is the partial pressure of the reactant A at a time t. Okay, so now we have the two values. Let me substitute the values here. Students, are you able to follow this? Hello, students? Are you able to follow? Yeah, good.
Yes, sir.
Right now. So, as I said before, initial concentration of the reactant is directly proportional to Pi. Concentration of the reactant at a time t is directly proportional to partial pressure of A. Now you know the value. What's the value? It is equal to 2 Pi minus Pt. 2 Pi minus Pt. Now I got these two values. So what is the rate constant? Rate constant K1 equal to 1 by T ln initial concentration of the reactant, which is proportional to Pi, divided by concentration of the reactant at time t, which is proportional to 2 Pi minus Pt. Okay, take this one. If a first order reaction is given like this, A giving B plus C, okay, and if total pressures at time 0, okay, and total pressure at a time t are given, okay, for this reaction, if it is a first order reaction, yes, you can calculate the rate constant by using the pressure values. Okay, note down. Is this clear, student? Any doubt? We'll do some numerical problems based on this once we finish up this topic. Then now suppose I'll take a second case. Suppose I have a reactant. Students, observe carefully. I have some reactant A, okay, which is in aqueous phase now. Let me take it in aqueous phase, aqueous medium, right, which reacts to give two product B in aqueous medium and C in aqueous medium. Okay, say for example, I'll take a reaction of this type. See, ethyl acetate, even you can take methyl acetate, nothing wrong on it. Methyl acetate, okay, reacts with the water, hydrolysis reaction in acid base, in acid medium. Okay, it will react to give acetic acid and methanol. Students, observe carefully. We have a reaction of this type. Now you know very well, in this reaction we'll take excess of water. Therefore this reaction follow first order kinetics. I have told you it's a very good example for pseudo first order reaction. What is pseudo first order reaction? If an higher order reaction follow first order kinetics, then it is called pseudo first order reaction. Originally it is higher order. Actually in this reaction it is second order. Order with respect to ester is 1 and order with respect to water is 1. So it is, we say that it is second order. But if you take excess of any reactant, then the contribution of that reactant in the rate expression, okay, can be removed or become negligible. So you can remove that. Okay. So since it's a first order reaction, rate of this reaction, students observe carefully, rate of this reaction is equal to rate constant times the concentration of the ester. This is the ester. So it depends on the concentration of the ester. Therefore we can write the rate constant K1 as, students observe carefully, it's a very important information, K1 equal to 1 by T ln initial concentration of the ester divided by concentration of the ester at a time t. Okay, but student, finding the concentration of the ester, okay, in a normal laboratory is a tough task. Okay, concentration of the ester, finding the concentration of the ester, okay, it's a difficult one. We need some special instrumentation techniques. Okay, but in this reaction we have an acid is produced, right? In this reaction acetic acid is produced. Since acid is produced, by using volumetric analysis, I can find the concentration of the acetic acid, okay, at various time interval. If you know the concentration of the one of the product, using that you can find the concentration of the ester at different time. Okay, how to do that? It's very simple. See what I'm going to do. Let me write the next page. What I'm going to do, see, initially we assume that we have a in a container we have ester with the water, okay, or we have ester alone. Just imagine like that. The reaction is not yet started. Okay, when the reaction is not yet started, students observe carefully, when the reaction is not yet started, actually in this reaction what we do is we'll take ester, we'll add water, we'll add some acid. Normally we add hydrochloric acid or sulfuric acid. Okay, because this is an acid catalyzed reaction, right? Now let us assume that at time 0 we have ester, we have water, we have only HCl. So if I titrate this mixture with the sodium hydroxide, I'll take sodium hydroxide in burette, some concentration of sodium hydroxide in burette. If I titrate this okay, at time 0, I'll take some small amount of this mixture in a conical flask. Students observe carefully. You take this mixture, assume that the reaction not yet started. At time 0 you take the reaction mixture in a conical flask, okay, then add a phenolphthalein indicator and titrate with sodium hydroxide. Okay, you will get some volume let us take that volume as V0. What is V0? V0 is volume of sodium hydroxide consumed at time 0. Students, observe carefully. Why this much volume is consumed? Because we have HCl. HCl is a catalyst here. Students, HCl is a catalyst. So this V0 corresponds to the concentration of HCl present in the mixture. Now what I'm going to do, at a time t, let us assume that the reaction started. Okay, once the reaction starts, what will happen? Ester will react, COCH3 ester, this is the ester, in the presence of acid. It will react with water and form acetic acid and methanol. Okay, now what happens? Acetic acid also is forming. This HCl, amount of HCl remains as such because it is a catalyst. You know very well. A catalyst is one whose concentration remains same. Whose concentration remains same in the mixture. So the HCl quantity remains as such. Whereas acetic acid is produced. Therefore, total concentration of the acid will increase. Am I right? Acetic acid is produced. Therefore, already we have HCl. Now you will get acetic acid. You will get acetic acid. Okay, up to some time t. Okay, now this mixture has HCl as well as acetic acid. Therefore, if you titrate now with the sodium hydroxide, okay, the reaction mixture consume more sodium hydroxide. Why more? Vt should be greater than V0. Why? Because we have HCl already, which is, since it is a catalyst, HCl concentration remains same. Okay, but as the reaction progress, you are getting acetic acid. Acetic acid is an acid. Therefore, total acid concentration increases. So if you titrate with sodium hydroxide, more sodium hydroxide will be consumed. Okay, so now listen, what's the data I have given? I have given at time 0, V0 is the volume of sodium hydroxide consumed, and at a time t, Vt is the volume of sodium hydroxide consumed. Now let us allow the reaction to complete. Students, observe carefully. Let us allow the reaction to complete. Reaction completed means all the esters get reacted. All the esters get reacted. So you will get in the final mixture. In the final mixture, we have HCl and we have acetic acid. Okay, at the infinite time or at the time of completion. Okay, let me take infinite time. Infinite time means that means the reaction has got completed. That's the meaning. Okay, now students, observe carefully. At a time t, we have some small amount of acetic acid, whereas once the reaction is completed, the entire ester become acetic acid. So acetic acid concentration is now very high. So the total concentration, HCl concentration plus acetic acid concentration, is very, very high. Therefore, at the time infinity, okay, if you titrate this mixture, final mixture with the sodium hydroxide, yes, the volume consumed, volume of sodium hydroxide consumed will be very, very large. Now, students, observe carefully. Let me go to the next page. Listen, I'll repeat. Sometimes they will ask questions like this. They'll give methyl acetate, okay, then they'll give water, then acid medium, okay, then acetic acid in aqueous medium, methanol in aqueous medium. For this reaction, sometimes they'll give information like this. Assume that it is a pseudo first order reaction. It's a pseudo first order reaction. I'm giving you the data. Pseudo first order reaction. For this reaction, listen, volume of sodium hydroxide consumed at different time intervals are given. I'm going to give time and volume of sodium hydroxide consumed. This data, these two data are given. Okay, at time 0, volume of sodium hydroxide consumed is P0. at time t, volume of sodium hydroxide consumed is Vt. At infinite time, that is at the completion of the reaction, volume of sodium hydroxide consumed is V infinity. Students, if these data are given, how to calculate the value of K1? That's the question. Okay. Students, observe carefully. This is very, very important. What we want is concentration of the ester at the beginning of the reaction and concentration of the ester at a time t. I have told you it is very difficult to measure the concentration of the ester, okay? But we can measure the acetic acid formed. Acetic acid is a product actually. We can measure the acetic acid formed at different time intervals by titrating the mixture with the sodium hydroxide. Okay, so initial concentration of the ester, students, can you tell me what is V infinity? V infinity is proportional to, let me write like this, it is the total concentration of the HCl, okay, where HCl is the catalyst. That concentration remains as such throughout the reaction, that concentration remains as such, plus the total concentration of the acetic acid that is formed, okay, at the completion of the reaction. Infinity means completion. Students, if all ester molecules reacted, you will get complete acetic acid, you will get the maximum amount of acetic acid, and that is this value. Okay, sum of these two is nothing but V infinity. What is V0? Students, can anyone tell me what is V0? What is V0? Anyone? V0 is nothing but volume of sodium hydroxide consumed at the beginning, okay, at time 0. At time 0 there is no acetic acid, correct? At time 0 there is no acetic acid in the reaction mixture. We have only ester, correct? Therefore V0 is actually proportional to concentration of HCl alone, which is actually a catalyst. Okay, now if I take the difference of these two, let me write here. I'll take the difference, that is V infinity minus V0. What will I get? What will I get? V infinity is concentration of HCl, okay, which is a catalyst, plus concentration of the acetic acid that is formed. In this case we got acetic acid that is formed, okay, at the completion of the reaction, minus V0 is concentration of the catalyst present at the beginning, and this value remains same. Why? Because HCl is a catalyst here. Therefore V infinity minus V0 is proportional to concentration of the acetic acid at the infinite time. Students, now tell me, in the reaction, see, I'll write the reaction. Methyl acetate, this is your ester, which reacts with water in the presence of acid, forming acetic acid plus methanol. See, students, observe carefully. If one molecule of ester react, I'll get one molecule of acetic acid. Am I right? According to the reaction, if one molecule of, students, are you listening? Hello? See?
Yes, sir. Yes, sir.
If one molecule of ester reacts, we get one molecule of acetic acid. Okay. So at the end of the reaction, see students, at the end of the reaction we'll get maximum amount of acetic acid that corresponds to the initial quantity of ester that is present. Okay, acetic acid at infinity means, okay, at the completion of reaction the total amount of acetic acid that is available. Okay, right? And you know very well acetic acid is formed from ester. So total acetic acid that is formed should be equal to the initial amount of ester present. So this V infinity minus V0 is supposed to directly proportional to concentration of the ester at beginning of the reaction. Student, note down, this is very important. Okay. Similarly, V infinity minus Vt, right? What is V infinity? V infinity is nothing but catalyst concentration plus concentration of the acetic acid, okay, up to till the completion of the reaction, or up to the final concentration of acetic acid, minus what is Vt? Vt is nothing but at the time t, okay, some volume of sodium hydroxide is consumed, that is due to concentration of HCl present, which is a catalyst, minus concentration of the acetic acid. Okay, actually I have to add these two and subtract, but I have given directly. This is up to time t. Students, observe carefully. These two cancel. Now total acetic acid minus acetic acid formed at a time t. That gives you, this will give you the concentration of the ester at a time t. It is proportional to concentration of the ester at time t. Okay, therefore we can write the rate constant as, so students, observe carefully, this is the final step. So concentration of the ester, okay, at the beginning of the reaction at time 0 is directly proportional to V infinity minus V0. Concentration of the ester at a time t is proportional to V infinity minus Vt. Now I can write the rate constant K1 equal to 1 by T ln V infinity minus V0 over V infinity minus Vt. Students, note down, it's a very important expression for rate constant of a first order reaction, right? And this is applicable for ester hydrolysis reaction. Ester hydrolysis reaction, you can use this expression to find the rate constant. See, if it is difficult to measure reactant concentration, okay, then if it is if it is possible to measure product concentration, any one of the product concentration at different time interval, using that data you can calculate the concentration of the reactant at different time interval. Okay, so this is a very nice example for first order reaction. Remember this, very important. Next, is this clear? Student, any doubt? So I have given gas phase reaction and reaction occurring in a solution phase. Now let me go to the next one. So in the first order reaction, student, this is another important one. Suppose let the initial concentration of the reactant is A0. Students, you tell me after the first half-life, let me put T of 1. T of 1 means first half-life. After the half-life, what will be the remaining amount of reactant? Remaining concentration of reactant in the mixture? Students, half-life means 50% will react, okay? So after the first half-life, what will be the remaining amount? Half of this, right? A0 by, yes, A0 by 2, okay? After the second half-life, anyone? After the second half-life?
A0 by 4.
A0 by 4, correct? A0 by 4, you are right. Right? After the third half-life?
A0 by 8.
A0 by 8, correct? So this is 2, this is 2 square. I can write this as 2 square, and here this is 8, we can write it as 2 cube, right? So now the question is, after the nth half-life, okay, say I have nth half-life, capital N, what will be the remaining amount after the nth half-life?
A0 by 2 power N.
A0 by 2 power N, okay, N, where N is the number of half-lives present in the number of half-life that the reaction progressed. Okay, now students, observe carefully. This is very important. So concentration of A remaining after n half-lives, concentration of A remaining after n half-life, okay, is equal to initial concentration of the reactant over 2 power n. Remember this relation, very important. Concentration of A remaining, okay, after n half-life, where n is the number of half-life, okay, n is the number of half-lives present in the given data. Take two. Now, just for understanding purpose, I'll give you a problem here. You try to do. Suppose a first order reaction is there whose initial concentration, let me give the initial concentration as 0.1 molarity. Okay, let the half-life of this reaction is 30 or 20 minutes. Students, observe carefully. I have a reactant whose initial concentration is 0.1 molarity and the half-life of the reaction is given. Now the question is, after say for example after 2 hours, what will be the remaining concentration of A in the reaction after 2 hours? Listen, in 2 hours, how many half-lives are there? Number of half-lives. For one half-life, it is 20 minutes. So 20 plus 20 plus 20, 60 minutes is 1 hour. So in 2 hours,
122.
correct? See, 2 hours means 2 into 60, correct? Divided by 20. How much I'll get? I'll repeat.
6, sir.
Yeah, how to find the number of half-lives? Listen, total time given divided by half-life. Simple. Total time given is 2 hours. You convert this into minutes. So 2 into 60. Half-life is given in minute only. So I'll put it into 20. So this is equal to 6, correct? See, number of half-lives is 6. In 2 hours, number of half-lives is 6. So what is the remaining concentration A? Use this formula. So remaining concentration A equal to initial concentration is given 0.1 divided by 2 power 6. Am I right? 2 power 6. Yes, take down. This is the remaining concentration of A. You have to divide by 2 6 times. Okay. If you want, you can do. But this is the method you should follow. Is this clear, student? If half-life is given and total time period is given, you can calculate the remaining concentration of the reactant, okay, after that time interval. Okay, if it is a first order reaction, yes, it is possible. Even for other order reaction we can calculate, but it is somewhat difficult. But for first order it is very easy. And this is very useful in the case of radioactive disintegrations. You know very well, in radioactive disintegration, the radioactive nuclei, okay, that radioactive disintegration, all radioactive disintegration follow first order kinetics. You may be knowing that. Anyway, I'll write here. Students, observe this carefully. All radioactive disintegrations follow first order kinetics. First order kinetics, note down. Very important. All radioactive disintegrations follow first order kinetics. Is this clear, student? Any doubt? Okay, right, take two. Effect of temperature, right, on the rate of the reaction. On the rate of the reaction. How temperature affects the rate of a reaction? Students, observe carefully. Rate, yes, change in temperature affects the rate of a reaction, no doubt in that. Okay, when you increase the temperature, in some reaction the rate will increase. Okay, if you decrease the temperature, rate will decrease. Okay, so rate of a reaction definitely depend on temperature of the reaction. Okay, so I can say that rate constant, right, depends on temperature. Rate constant is a function of temperature. Note down. Rate constant of reaction is a function of temperature. Right? Now, students, observe this carefully. Suppose if we plot potential energy of the reactants and products in y-axis and reaction coordinate in x-axis. Reaction coordinate. Reaction coordinate means it may be a bond length, it may be a bond angle, whatever it is. Some reaction coordinate. Reaction coordinate, I repeat, students, any quantity that is changing, okay, any quantity of the molecule that is changing during the reaction. In a molecule, there may be bond length, there may be bond angle, right? During reaction, the bond length may change, bond angle may change. You take any one variable, any one coordinate, and plot that. Potential energy versus reaction coordinate. Okay, if you plot, you will get what is called potential energy diagram. This diagram is called potential energy diagram. Students, observe carefully. This diagram is called potential energy diagram. For a reaction, see, initially we have reactant. The reactant will have some average potential energy. Let it be let be this value. This dot indicate average energies of the reactant. Now, when the reaction starts, suppose I'll take a gas phase reaction. Students, observe carefully. In a container, we will take gaseous molecules. Right? At the beginning means no reaction is not yet started. Okay, we have only reactant molecule, and the average potential energy of the reactant molecule is this. Now, if I allow the reactions to start, what will happen? The gas molecule starts to collide. Because of collision, students, observe carefully. Molecule, one molecule and another molecule, they collide. Because of collision, the energy of the reactant molecule starts to increase. Overall energy of the molecule increases, reaches a maximum. Then once the molecule gets enough energy, when they hit, listen, suppose if the molecule have low energy, students, observe carefully. If the colliding molecules have low energy, then that collision is not a fruitful collision. Okay, it's not fruitful. Whereas if the same reactant molecule have sufficient energy, minimum energy required for the reaction, okay, let me call that as activation energy. Students, observe carefully. Molecule may have energy above this also. But what is activation energy? It is the minimum energy required. If the molecule have that sufficient energy, and if they hit, if they collide, yes, you will get product. It is called fruitful collision. Fruitful collision. Students, what is unfruitful collision? What is fruitful collision? Listen, in the gaseous state, reactant molecule keep on undergoing collision. Okay. All collision will never form product. That's the point. All collision will never form product. For collision, listen, if the reactant molecule have sufficient energy and if they collide, then only they form product. So suppose if I have reactant molecule, see the diagram. If suppose I'll take reactant molecule at this point, they have only this potential energy. That potential energy is not sufficient. If these molecules undergo collision, they never form product. But what happens because of continuous collision, the energy of the reactant keep on increases and reaches a maximum. Once molecules comes here, that means these molecules have this much energy. Okay. Once the molecule has that much energy and if they undergo collision, yes, they'll form product. Okay, let us assume this is the product. So this is the average energy of the product and this is the average energy of the reactant. Students, observe carefully. Listen, to form product, the reactant must have this minimum energy at least, which we call as the activation energy, EA. Note down, student. Activation energy. Can anyone tell me what is activation energy now? What is activation energy? It is the minimum energy required. Okay, it is the minimum energy required by the reactant molecules, okay, to form product. It is the minimum energy required for the reactant molecule to form product. Okay, you may have some molecule may have energy above this also. Some molecule may have energy above this also. Those molecules are also available, but they also form product, no doubt in that. But if molecule have this less energy, this is the minimum energy, right? This energy is somewhat maximum. This energy is somewhat maximum. Okay, what is activation energy? It is the minimum energy required for the reactant molecule to form the product. Okay, so what is activation energy? Activation energy is the minimum energy required for the reactant molecules to undergo collision and form product. Okay, take down. Is this clear, student? Any doubt? That is called the activation energy. Right now, let me go back again. See, I'll give the plot again. See what I'm doing. We are plotting potential energy in y-axis and reaction coordinate in x-axis. Okay, reaction coordinate. Students, observe carefully. This is the average energy of the reactant and this is the average energy of the product, and we have the potential energy diagram which appears like this. Okay, listen, from the 0 point to this maximum, okay, this energy is what we call as threshold energy. This energy is called threshold energy. Okay, and what is this energy, student? Can anyone tell me what is this energy from 0 to R? That is the average potential energy of the reactant. Okay, if I subtract, students, tell me what quantity I'll get. Threshold energy minus average energy of reactants. If I subtract this, what will I get? From threshold, this is the threshold, I am subtracting this quantity. Yes? Yeah, you'll get activation energy. So activation energy is nothing but threshold energy minus average energy of the reactant, and this is nothing but the activation energy. Now students, let me ask you a question. Are the molecules in the reactant have only activation? Is the activation energy is the maximum energy for the reactant molecule to have in the vessel? I repeat my question. We have lot of reactant molecules in the vessel. My question is, is the activation energy is the maximum energy attainable by the molecule? No. Reactor molecule can even attain energy more than that. Then what is EA? EA is the minimum energy required. Okay, if molecule has this much energy is enough for the reaction to occur. If the molecule have more than that, no doubt the molecule will form product. Right? But if the molecules have energy less than activation energy, those molecules do not form any product due to collision. That's the point you should keep in mind. Okay, so what is meant by active molecules? Active molecules are molecules, they have energy equal to activation energy or more than that. Okay, now we want to know what fraction of active molecule present in a mixture. Okay, say I have a reaction mixture. So what is the fraction of active molecules? Active molecules, right? At some temperature, at T, at some temperature T, at some temperature T, capital T. Here I'm what I'm saying that T is the temperature. At the temperature T, what fraction of molecules are active? Active means they have energy. What is meant by that? They have the energy of the molecule. Molecule may be greater than or equal to the activation energy. Students, observe carefully. What is meant by active molecules? Active molecules means, listen, molecules having energy either equal to EA or above that. Those molecules are called active molecules because they undergo collision and form product. So what is the fraction of active molecule present? Listen, this is nothing but, student, observe carefully, this is nothing but equal to e power minus EA by RT. Note down. Exponential power minus EA by RT. This we get from Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution. From Maxwell-Boltzmann distribution, we get this quantity. Take note. E power exponential power minus EA by RT will give you fraction of active molecules at temperature T. So at temperature T, what fraction of active molecule is present? That you can calculate using this data. Right? Now, using this idea, scientist Arrhenius gave an equation to calculate or to understand the effect of temperature on the rate of the reaction. What is that? Listen, rate constant of a reaction, rate constant K is equal to, students, observe carefully. Initially, scientists thought that reaction occurs only because of collision. If collision takes place, reaction will occur. So they thought that rate constant is directly proportional to, right, collision frequency. Okay, let me represent that as A. What is A? A is called number of collisions that occur in 1 second or in 1 unit volume. In 1 second, in 1 unit volume. So people thought that rate constant is directly proportional to number of collisions that occur per unit volume, per unit time. Okay, but later it was found that not all collisions giving product. Students, observe carefully. Initially they thought that rate constant is directly proportional to number of collisions. Okay, if number of collision is the only reason for the rate, then in a particular time, okay, you might many collisions may occur in the reaction mixture, but the rate is less. Why? Because all collisions are not fruitful collisions. All collisions are not fruitful collisions. Only few collisions are fruitful. Therefore what scientists did was, listen, some other factor also decides the rate of the reaction. What is that? We need to find the rate of the reaction depends on fraction of molecules, depends on fraction of active molecules. See, it not only depends on collision, it also depends on fraction of active molecule present at the temperature T.
Sir, what is
Therefore,
A?
by combining these two, we can write
Sir,
K is equal to,
Sir, Ashika is calling.
pardon?
sir, what is A, sir?
Ashika,
Sir,
little louder.
Ashika is calling you, sir.
Hello, Ashika? Be louder, ma'am. Yeah, I'll tell you. A is the number of collisions, okay, per unit volume. Let me use the word like this, per unit volume per second, right? But I'm going to give you a different term here, but right now just keep this in mind. Okay, rate constant of reaction depends on the number of collisions per unit volume per second. Okay, and K, rate constant, is also depends on fraction of active molecules present in the reaction mixture. So by combining these two, okay, Arrhenius gave a relation. Scientist Arrhenius gave an equation called Arrhenius equation, according to which rate constant K is equal to the frequency factor A into e power minus EA by RT. What is this? This will give you fraction of active molecules, and this will give you number of collisions that occur. Okay, take it one, student. So this A is called pre-exponential factor, because this is exponential. So this is A is present in front, so it is called pre-exponential factor, also called Arrhenius frequency factor. Okay, pre-exponential factor, also called Arrhenius frequency factor. And what is EA? EA is called activation energy. EA is called activation energy. Okay. Students, is this clear? Any doubt? And this is called the Arrhenius equation. Let me write the equation again. According to Arrhenius equation, rate constant K is equal to A into e power minus EA by RT. This is the Arrhenius equation, which gives you the relation between rate constant and temperature of the reaction. Okay, if you change the temperature, then the rate will change, the rate constant will change. Okay, student, this is called pre-exponential factor or frequency factor, Arrhenius frequency factor, and this quantity e power minus EA by RT will give you fraction of active molecule at temperature T. At temperature T, okay, what fraction of molecules are active molecules? That you can find that using this expression. Okay. Listen, student, what is fraction of active molecule? See, number of active molecules divided by total number of molecules, that's all. Na is number of active molecule, capital N is the total number of molecule, Na by N is nothing but e power minus EA by RT. So if you want to know fraction of active molecule in a reaction mixture, you can calculate using this formula. And if you know the fraction of active molecule and if you know the frequency factor, if you multiply these two, you will get the rate constant. This is what we call as Arrhenius equation. Okay, you know what is the meaning for activation energy now, students. I'll just finish off this and I'll stop. I'll just give this information and stop. See this. I am plotting potential energy versus reaction coordinate. Student, observe carefully. Versus reaction coordinate. Okay. In some reaction, this is your average energy of the reactant, this is the average energy of the product. In some reactions, students, observe carefully, reactants have higher energy, product may have lower energy. In some other reaction, reactant may have lower energy, product may have higher energy. Okay, we have this kind of reaction also. Students, observe carefully. Whenever your product have lower energy, then this much energy, okay, of the reaction, or this much energy of the molecule will be dissipated as heat. Okay, so it is called exothermic reaction. In this case, delta H is negative. Students, observe carefully. Whenever product has lower energy compared to reactant, in this type of reaction, okay, excess energy is released as heat, because your reactant has higher energy but your product has lower energy. That means in the when the reactant form product, some amount of energy should be dissipated out. Okay, so this reaction is called exothermic reaction. If product has higher energy compared to reactant, in this case, to form product, reactant require energy. Therefore, energy is absorbed. You will get this type of reactions are called endothermic reactions. So for exothermic reaction, delta H is negative. This is for exothermic reaction, exothermic, and for endothermic reaction, delta H is positive, endothermic. So by just seeing the potential energy diagram, okay, you can easily identify whether it is an exothermic reaction or an endothermic reaction. Is this clear, student? Any doubt? Students, is this clear?
Yes, sir.
Right.